Okay, thank you. So what I'd like to talk about today is to go beyond talking about some gas processes and start saying something about how the solid material in protoplanetary disks both reacts to the gas phase processes and then also has some separate dynamics of its own. Okay. So to some degree, this is going to involve us having to start discussing some sort of complicated and slightly messy questions of the physics of real materials. So in protoplanetary disks, the solid material is either rocky materials like silicates, or it's icy materials, so water ice with various other things added into the water ice. And in some places, it really matters what these materials are made of, right? It's more than them just being spheres with a particular radius, with a particular density. The actual physical properties of the materials actually matter. So I'll show just a handful of slides discussing some aspects of that, but that's really mostly, let's say, an experimental or certainly a numerical kind of problem to look at. We can't really do very much analytically when dealing with those kind of complexities. So I'll mostly focus on the aspects which are somewhat cleaner and where we can really say something without really needing to go into the details of what the solid material in the disk is. Okay, but before getting to the slides, I just want to emphasize one thing, which is if we have solid material within the disk, it's interacting with the gas, how does that interaction take place? Okay, so let's imagine a very simple toy situation. We imagine that the solid component of the protoplanetary disk is made up of spherical particles with uniform density, and they're just interacting aerodynamically with the gas disk. Okay? So the sort of picture you might have is here we have some particle, let's say that has radius s. It has material density, so the actual density of the stuff that makes up the particle, call that rho m. And therefore it will have mass, which will obviously just be m, which will just be the normal expression. Okay. So we have a particle of particular density and a particular size. And it's interacting with the gas because it has some relative velocity, delta v, with respect to its local gas. Okay. So if you think about this, this is just an aerodynamic situation. And the situation you might be most familiar with is one where we have a hydrodynamic flow of gas which comes around this sphere. Okay? So that circumstance is described as Stokes drag, and it's a hydrodynamic process. The fluid comes in, flows past the sphere, and then as a result of that, we get a drag force on this sphere, which obviously acts in the opposite direction to the direction of the velocity. Okay, so we have some F drag. Okay, so if we have this situation, how do we expect this drag force to scale with this relative velocity? V squared, right? So in this case, the drag goes as v squared. Okay. So this is the environment I think we're most familiar with, right? If you're a keen cyclist, you can get into a regime where you are cycling fast enough that the aerodynamic drag is the main component that is making it difficult to go faster, and you know that it gets increasingly difficult to go faster because of this delta v squared dependence of the drag force. Okay. However, we're familiar with this because this is a hydrodynamic situation. This applies when the mean free path of the molecules in the gas is small compared to the physical size of the object, which of course is definitely satisfied in the sorts of terrestrial applications we're thinking about. Okay. Now, in protoplanetary disks, this can certainly take place. If this object is an asteroid and it's moving with respect to the gas, it will have this kind of hydrodynamic flow around it. However, if we're thinking about earlier stages where the particles are smaller, the most common situation is that the particle is actually smaller than the mean free path in the gas around it. Right? We said yesterday that the sorts of numbers, even in the dense parts of protoplanetary disks, the mean free path might be centimeters or even getting on for meters. If we go to the very rarefied regions at the outside, the mean free path will be even larger than that. Okay. So in that case, from the point of view of the particle, it doesn't really see a hydrodynamic flow because actually we don't have collisional processes in the gas on the scale of the particle. Okay. So the other regime is described as Epstein drag. So we still have a particle which is moving at some delta V with respect to the local frame in which the gas is stationary. But now instead of a hydrodynamic flow, you should maybe think of it that we have a bunch of individual molecules surrounding this particle. And these molecules are going to actually be moving typically rather fast compared to this delta V. Okay? And what would happen simply is that some of these molecules will hit and bounce off the front side. Those will give a force in the backwards direction. Other molecules will hit from the back side, and they'll give a force in the forward direction. Okay? So if delta V was 0, this would be basically the setup for Brownian motion. This particle would be being kicked around by the random collisions of these molecules. Okay? And if we have a delta V here, there will be a slight preference for more collisions to occur on the front side than on the back side. And so we will get an aerodynamic drag force that acts on the particle, but it won't be due to this sort of fluid motion, which is what occurs in Stokes drag. Okay? So if you think about that, you can fairly easily convince yourself that in this situation, this drag force that we get, which opposes the motion as usual, is not quadratic in the velocity difference, but it's just linear. Okay. So the expression for that is that F drag is minus, let's write this somewhere else, minus 4 pi by 3 rho s squared v thermal delta V. Okay, so rho is the density of the gas that the particle is interacting with. Delta V is its relative velocity. S is its radius. So obviously this depends on the cross-sectional area that the particle presents to the gas around it, and V thermal is just the thermal speed in the gas. Okay, so you can convince yourself that this is delta V with just a very simple model where you imagine sort of two streams of colliding molecules, some hitting the front and some hitting the back. You get the right prefactor by considering the geometry and assuming a Maxwellian distribution for the collision velocities. Okay. So you get that drag force, and it's, as I say, it's linear. So it just has a different behavior from the hydrodynamic situation. However, this actually is rather nice and rather convenient for protoplanetary disks because it means that if we consider the interaction between particles and the gas, there's just one number which characterizes how strong that aerodynamic coupling between the solid component and the gas component is. Okay? And that number is described as the stopping time. And the way to think about this is to imagine that we have this particle, it's moving through the gas, with some delta v, there will be some characteristic timescale on which this momentum associated with the relative velocity would be reduced as a result of the aerodynamic coupling. So the particle, if you like, if nothing else happened, would just come to a stop and slow. Okay, so we could write that as being T sub s, which would be this m delta v divided by f drag. Okay, take the magnitude of that. Okay. And what's nice about this Epstein regime is that the drag force is linear in delta v, and therefore this stopping time doesn't depend on the actual velocity, the relative velocity that the particle has with the gas. Okay? And that wouldn't obviously be true if we were in the Stokes regime, because then the drag force would be quadratic in delta v. Okay? So it's just one number. Okay, so if you plug in the expression for the drag force and the mass of the particle, so 4/3 pi s cubed rho m, then this quantity, this stopping time, takes a simple form. It's just the ratio of the material density of the particle, the density of the stuff it's made of, so that might be 1 gram per cubic centimeter if we're dealing with water ice, divided by the density of the gas, and then it's the size of the particle divided by the thermal speed. Okay. So that's the key physical quantity which determines if we have particles of a particular size orbiting within gas of a particular density and a particular temperature, how strong the aerodynamic coupling actually is. Now, very frequently, a more useful way of expressing this is not in terms of this dimensional quantity, but in terms of a dimensionless quantity. So we take this timescale and we take the ratio of this timescale to some other timescale that we're interested in the problem. Okay? So if you think we're imagining a gas orbiting the star in a disk at some radius, what other timescale might we think of as being a useful one? Period time, right? So we have a particular radius. The most basic timescale perhaps is just going to be the orbital timescale around the star. Okay? So we can make this dimensionless by just scaling that out. So we'll call that tau sub s, which would just be this physical stopping timescale multiplied by omega. Okay, so that would just be taking the ratio to the orbital time with a factor of 2 pi. So this is just a pure number, and if tau sub s is very small, physically that means we have small particles which are going to be very tightly coupled aerodynamically to the gas. If tau sub s is large, we're dealing with big objects which feel some aerodynamic forces, but there may be perturbations on a Keplerian orbit. And of course, the most interesting situation is tau sub s of order unity, where the coupling is sort of marginally strong and it operates on basically the same time scale as other forces within the system. Okay. So I think in everything I'm going to say today, I'm going to use this definition of the dimensionless stopping time. It's also described sometimes as the Stokes number. You can potentially ratio this to other timescales. So if you had a turbulent eddy, a vortex, or something like that, you might be interested in the ratio of the stopping time to the time it takes to circulate around the eddy, right? So you might usefully think about other dimensionless quantities you could construct in that way. But for sort of the global picture, what we're normally interested in is just this ratio with the orbital speed. Okay. And there's sort of a number of different ways this might work. Okay? So imagine that you're sitting in the disk, you're a particle sitting in the disk at some height above the midplane. Okay? So we said on Monday that for the gas in the disk, you have a balance of forces there where the vertical component of the stellar gravity is trying to obviously move the material towards the midplane, and that's resisted by a pressure gradient. Okay. Now, if we have a solid particle that's sitting up there, it will still have the vertical component of stellar gravity, but it won't feel the pressure gradient. So if nothing else happens, we would expect, let's say, dust or small particles to start to settle vertically towards the midplane and form a thinner dust disk embedded within the larger gas disk. Okay? So that will be dust settling, and locally that means the solid to gas ratio will be enhanced in the midplane and will be depleted as we go to the disk atmosphere. Okay? Now there will also be collisions, which we'll say more about later, and then another thing which we'll discuss is that if we're just orbiting there, even at the midplane, there will be a radial drift which will tend to cause the particles to move towards the star. Okay? You can think of that in various ways. The very simplest way is to imagine actually quite a large object. So imagine we're in the regime where this tau parameter is much larger than 1. In that case, the aerodynamic forces are perturbations, and the orbital speed of that large boulder or asteroid perhaps is basically the Keplerian speed around the star. And we said on Monday that the speed of the gas orbiting the star is very close to Keplerian, but it's typically a little bit slower because there's a radial pressure gradient which provides some support against gravity, right? And that was a small number. That was this 100 meters per second or something like that, even quite close to the star. So it's not a large number compared to the orbital velocity. But what it means is that this particle, this boulder, will actually be moving forwards with respect to its local gas. So it will feel a headwind. That will give an aerodynamic drag. It will lose angular momentum, and it will start spiraling in towards the star. Okay, and we'll work out how that goes a little bit later. Okay, but let's start with this simplest thing of dust settling. So here we have this particle sitting above the midplane of the disk. It starts falling towards the midplane under the action of gravity, which is not opposed by a pressure gradient. Okay. Obviously, once it starts falling, it picks up a delta V, feels some drag, and therefore there's a drag force which is opposing the settling. Okay. Now you can work out the numbers quite straightforwardly here, and what you find is that the particle will very quickly, in most cases, at least if it's a small particle, come to terminal velocity. Okay. So it'll come to a situation where the downward force of gravity is just being balanced locally by the upward force due to the drag force. So its speed, the acceleration stops and it just falls at a constant speed. Okay. So here's the expression for the gravitational force in the limit where the height, z, is small compared to the radius. This is the same expression we had for the gas hydrodynamic equilibrium. Here is the magnitude of the drag force in this Epstein drag regime. Okay. So you set those two things equal to each other and solve for the settling speed, and this is what you get. Okay. So the settling speed is linearly proportional to the height above the disk midplane, because gravity increases as we go away from the midplane. There's no vertical gravity at z equals 0, and it depends very strongly on obviously the gas density which the particle is embedded in. Right? When you're high above the midplane, the gas density is very low, the terminal velocity is high. As you get close to the midplane, that settling speed goes down. And it's also linearly proportional to the size of the particle, the radius s. So if you consider some numbers, let's imagine really quite small particles, so 1 micron sized particles. So those might be sort of dust grains that have been captured from molecular cloud when the disk formed, or small particles that have condensed out of the gas phase as the gas has cooled. Place them at some particular place within the disk. This settling time works out to be about 100,000 years. Okay. So it's not incredibly short in terms of velocity. It's quite a small velocity, a millimeter per second or something like that. But it's nonetheless fast compared to the disk lifetime. Okay. So one immediately sees that this kind of process ought to be important within disks. We don't expect the gas and the dust to remain perfectly well mixed, because basically different forces are acting on the two components. Okay, so that's a simple situation. We just have one particle, one micron-sized dust grain, and there's nothing else in the gas. It just settles down towards the midplane on some timescale. Okay. Now, an interesting toy model you can think about, which actually was originally thought of by Viktor Safronov in the 1960s, or even earlier than that, is a situation where you have a bunch of particles of different sizes, and they're all sort of settling collectively together towards the disk midplane. Okay? So let's imagine one circumstance where we have one particle that's a little bit larger than the rest, and so it's settling, and then there's a sea of smaller particles which it's sort of settling through. Okay? So this would be something like a sort of raindrop model. Okay? We have different particles, they're dropping, and then as they're dropping, the ones that are dropping the fastest can sweep up the smaller ones, which are dropping at a slower rate because they're smaller and they have a smaller settling speed. Okay? So this would be the picture. A large particle dropping fast. As it drops, it hits a bunch of smaller particles, which because they're smaller, have greater aerodynamic drag, more surface area to mass, so they're falling more slowly. Okay? So obviously what happens here depends on what happens when two particles collide. Okay? But for this toy model, which Safronov considered, let's just assume that there's perfect sticking. So anytime two particles physically touch each other, they adhere. Okay? So in that case, you have a simple situation. For the large particle, the rate at which it's falling, the settling speed, dz dt, is just the expression we had on the previous slide. And then the amount of mass that particle picks up is just the projected area of the particle, pi s squared, times this settling velocity. So let's assume all the other particles are very small, so they're barely settling at all. We don't need to worry about that. And then F here would be the ratio, the local ratio between the solids and the gas, and rho would be the gas density. Okay? So we have two simple coupled differential equations, which will give us an expression for how the mass of this large particle grows as it falls towards the midplane and simultaneously sweeps up all the small particles that it encounters along the way. Okay? And if you do that, you get a plot that looks like this. So here's the height above the midplane. Here is the particle size in microns, and here is time in years. Okay? So what we've done here, this has some parameters going in about what the gas disk looks like, which are not too important. But what we've considered is particles that initially start at 5 scale heights above the midplane and are quite small. So they vary between 1 micron and 1/100th of a micron. Okay? So either quite small or really very small. And the key point is that for all of these particle sizes, as the particle starts settling, if it can keep on accreting the smaller things efficiently, as it sweeps them up, it becomes more massive. That means it wants to settle faster, and then it becomes even more efficient at sweeping up more small particles that are in the way. Okay? So what happens is that as it falls towards the midplane, it grows by actually several orders of magnitude in particle size, and therefore many orders of magnitude in particle mass. Okay? And the time scale, as you can see, is quite short. Okay? So before, for 1 micron sized particles starting at 1h, we were talking about 10 to the 5 years. By assuming that we can hit other particles and grow in mass, we've actually reduced that timescale by 2 orders of magnitude. And as you can see here in this toy model, actually it doesn't depend on the initial conditions because these tracks are convergent towards a single solution. Okay? So, one thing, so this is a very toy model, but one thing it immediately says is that if particles can be fairly efficient at physically sticking together when they collide, the basic timescales on which very small things can grow at least to small macroscopic dimensions, sort of the size of millimeters and so forth, is basically not a problem, right? Things can happen quite quickly within the disk environment. Okay, so that's sort of good in some sense, but it's also not consistent with what we see, okay? Monday, we showed some ALMA pictures of protoplanetary disks, and I said what you're looking at there is thermal emission from, let's say, millimeter or roughly millimeter size dust grains. And some of those disks have been sitting there for millions of years. There's a lot of dust there. There's also small dust, which is what we see in Hubble Space Telescope images of scattered light from those disks. So in real disks, sure, perhaps a lot of material does grow to millimeter sizes, but there's also small material which also survives for millions of years, not hundreds of thousands of years, as that toy model would suggest. Okay? Moreover, if you look at a disk that's sort of almost edge on, we maybe see that the solid material is thinner than the gas, but it's not really a razor-thin sheet in the equatorial plane, which again would be what that toy model would sort of suggest. So something else must be happening, and one possibility, the most likely possibility, is that if the disk is turbulent, then the turbulence will act to stir up the dust and preclude it from settling into a very thin sheet at the midplane. Okay? And you can model that quite simply with an advection diffusion equation, so an equation for the evolution of the dust density. So this is now not the material density of the dust, but rather it's sort of smoothed out its volume density. So take the solids in the dust, just ask how much mass you have per cubic centimeter. And if you just have settling, you'll have an expression like this on the right-hand side, which is basically the same expression we've already derived. But then, at least in a semi-quantitative way, you can add a diffusion term where the quantity that's diffusing is the concentration, the ratio of the dust the dust density to the gas density. So the idea would be that diffusion is trying to equalize this concentration in the vertical direction, but then settling is trying to oppose that, and so you can set up some kind of equilibrium where those two processes are in balance. Okay? So, of course, this depends on knowing what this diffusion coefficient actually is. The simplest thing you can do is to assume that the turbulence that is producing angular momentum transport, so that's this kinematic viscosity nu, is of the same order of magnitude as the diffusion component that is being produced by that turbulence. Okay? And that is maybe not too bad an approximation if you're really dealing with quite small dust grains that are quite tightly coupled to the gas. If you deal with much larger dust particles or much larger particles where this tau becomes larger than unity, then that's no longer true. Okay? In that case, there's a tau to the -2 or thereabouts suppression of the dust diffusion coefficient. But with this simple assumption, you can derive an equilibrium scale height of the dust compared to the gas, and it depends on this Shakura-Sunyaev alpha, which is characterizing the viscosity, and on the dimensionless friction time T stop here. Okay? So if you're in a situation where you're dealing with small values of alpha, so disks that are not very turbulent, and relatively large particles, you can get quite thin dust layers. Okay? But if you're dealing with more turbulent disks, obviously the turbulence is quite efficient at suspending small particles vertically within the disk. Okay? Now, what's important here is that this ratio of these scale heights involves this square root factor of this ratio of dimensionless parameters. Okay? And what that means is that it's actually quite hard to get into a parameter regime where the dust density, the dust thickness, is really much, much smaller than the gas thickness, right? Even if we had, let's say, alpha of 10 to the -4, which is quite a weak value of the turbulence, then let's say for this, if we put this dimensionless stopping time at 10 to the -2, then we've got like a factor of 10 here between the dust scale height and the gas scale height. So we can make the dust quite thin, but it's quite hard to get it to a really razor-thin sheet. Okay, so this is just writing down what I just said in words. It's quite hard to get really thin dust layers. Okay, so suppose we take alpha of 10 to the -4, which would be certainly quite a low value for protoplanetary disks, we think. If we take these critically coupled particles with tau stop of 1, then we get a factor of 100 in the thickness of the particle layer relative to the thickness of the gas layer. So that's significant, but as we'll come to a bit later, what it means is if we consider what the average value of the dust or the solid to gas ratio is in protoplanetary disks, that's about 1%. So if we take sort of a cosmic abundance of materials and condense out everything we can, we get about 1% of the total mass is in solids, the other 99% is in gas. Okay? So if we had that material uniformly mixed throughout the disk, the solids are really a trace component. Okay? Even in this best case where we have low turbulence and these critically coupled particles, we can't actually settle, or we can just about settle to the point where locally the solid density is sort of comparable to the gas density. Okay? So we can get to an interesting regime where these two densities are equal, but it's quite hard to push to a regime where the solids are immediately much denser than the gas. And that will be important later, because some models for getting to larger objects, for making planetesimals, kilometer-sized bodies, require us to be in strongly solid-dominated conditions. Okay, so where the solid density is actually exceeding the gas density, maybe by a factor of 100 in the other direction. So the solids are really dominant. And there's then, okay, so you could say we don't know much about turbulence in disks. Okay, that would certainly be a true statement. So I've said alpha of 10 to the minus 4 is a sensible number, or even lower than a sensible number. You could obviously say, maybe I'm wrong about that. Right? Maybe alpha is much lower. Maybe it's 10 to the minus 10. Okay, so there's basically no turbulence whatsoever in the disk. And obviously that would change this conclusion. However, even if we had such a disk which in the gas phase was not turbulent, it would be difficult to sustain that situation once the dust layer gets thin enough. And the basic picture would be that we imagine we get a very dense dust layer in the midplane, and then what would happen is that the dust, which would be trying to orbit the star at the Keplerian velocity, would start sweeping around the gas that it's entrained with at that same speed. Okay? So then what we would have is that in the midplane, both the dust and the gas would be moving at close to the Keplerian speed, but then when we go to the particle pore region that's above the layer, the gas will have its pressure gradient, which is partly supporting it against gravity, and it will be moving a little bit slower than the Keplerian speed. So in that situation, we would have a vertical shear in the velocity, in the azimuthal velocity, and if that vertical shear becomes strong enough, it will be unstable to developing Kelvin-Helmholtz instability. So even if there were no processes that intrinsically generated turbulence in a purely gas phase disk, having a very settled particle layer would give another reason for generating turbulence on its own. Okay? And here we're not talking about the MRI or complicated things to do with non-ideal MHD. We're just thinking about Kelvin-Helmholtz turbulence, and we think we really do have a pretty good idea of the conditions under which that process would take place. Okay, so that was what I wanted to say for the moment about settling. What about collisions? Okay, so we said that if collisions are perfect, so in the sense that whenever two particles collide, they stick, then that actually implies that growth occurs on really quite a short time scale. Okay, so is that true? Okay, well, there's really only one thing that you can say, sort of completely analytically or in an elementary sense, about this, which is that sticking of things that are colliding with each other at a constant velocity generally becomes harder as the particles become larger. Okay? And the argument is just, imagine we have two particles, mass m, have some relative velocity delta v at large distances. They come and collide. When they collide, there's basically three things that can happen. They can stick, they can bounce, or the collision can be so energetic that it actually breaks one or more of the particles up into small pieces. That can be a fragmenting collision. And the key point is that when the two particles collide, there's some surface area, there's normally a fraction of the total particle area, that is actually physically in contact at the point of maximum compression during the collision. Okay? And that contact area is associated with an energy, which is due to molecular forces between the particles that are making, between the molecules that are making up these solid particles. And that adhesive energy depends on the area of the contact patch. Okay? And the point is simply that the mass of the particles goes as the cube of the volume, whereas the area available to stick them together goes as the square. Okay? And if we want to actually keep them stuck together, we obviously have to dissipate some of the energy that is in the colliding objects. And that energy grows as the mass, but the area we're trying to do this over just grows as the square of the size. So as we go to bigger things, we have to be more efficient at dissipating the collision energy so that they don't actually just bounce back out and remain unstuck. Okay? So material forces, the fact that things sticking really requires actual material forces to hold them together, favor sticking at small particle size, and things get harder and harder as you get larger. Okay? So that's obviously a general conclusion, but it doesn't say everything, because obviously what the material is made of matters a lot. Okay? And there's sort of two circumstances you can think of. If you go to the desert and pick up a couple of rocks and start throwing them together and hoping that they will stick, you will generally find, I think, that process is not going to be very efficient. You'll be in the desert a long time waiting for the boulders to stick together. On the other hand, if you have snowballs, especially if it's not really cold, if you have like wet snowballs and you throw those together, if you're not too violent about it, you have a reasonable chance of making those things stick, okay, at the same size and the same velocity. Okay. So the material matters a lot. Okay. And in protoplanetary disks, close to the star, you're dealing with basically rocky kind of things. Far out, you're dealing with icy kind of things. Of course, the temperatures and pressures are much different from snowballs, but nonetheless, you might expect there to be a physical difference in what is happening. And indeed, that's what people find, right? The outcome depends on the collision speed, depends on the size of the particles, what they're made of. It also depends on whether they're really sort of homogeneous objects, like homogeneous spheres, or whether they're like very fluffy aggregates which have a lot of spare space in them. Okay? So you might think a very porous object is a very fragile object, and in some sense that's true. But if you have a very porous object, then actually the rearrangement of that object, the compression of that object when it hits something else, can dissipate a lot of energy. Right? It can sort of act like an airbag in some sense. Right? It can absorb a lot of energy and not break it completely apart. So porosity is not necessarily a bad thing if you want things to stick together. But it's a complicated situation, and it's primarily studied experimentally. Okay, so in drop towers, where you fire a projectile, a container up in a tower, and then flies to the top and falls back down again, and for a while it's in 0G. Aircraft, suborbital rockets, and so forth. Okay. So here's just an example of that. So this is kind of fun stuff, right? Because basically it involves throwing together sand or things like sand or snowballs in the lab, quite small scale, trying to see whether they stick. So this is a review by Jürgen Blum and collaborators in annual reviews now a long time ago. This is like a little video of one of their experiments. This is just a few seconds in real time where you take a sand pile, basically, so silicate material, and then you fire in smaller bits of sand and look at it with a high-speed camera, and you ask, does one clump of sand stick to the other clump of sand? And you do this many times and vary the impact speeds. At some point I visited Jürgen Blum. He actually showed me that they have some smaller things that are in their own lab where you just drop things in an evacuated glass cylinder, and it's actually great fun to look at. He also showed me a much better video, which I haven't been able to find on the web. So this is done with a very high-speed camera. This is like 100,000 frames a second, and so such cameras are very expensive. And on one of these drop tower experiments, the camera wasn't properly secured, and so when it hit the bottom and the thing was decelerated, the camera just came through and smashed through the experiment and destroyed the camera. He had a video of that, which was both fun and horrifying to look at. Okay, so there's a big parameter space here. So these experiments are, a bit tricky, a bit delicate, and there's also a big parameter space, because in protoplanetary disks you can be interested in things that are micron-sized, you can be interested in millimeter-sized things, then of course ultimately we want to make things that are much bigger than that, meter-sized. Okay, so this is from that same annual review, and here what you have is the diameter of one colliding object, and then the diameter of the other colliding object. And then these contours here, I'll come to later, give an idea of, from sort of theoretical arguments based on turbulence, of what the collision velocities between those objects ought to be. Okay? And so ideally, one would like experimentally to cover this whole parameter space. Okay? And these rectangles here show different real experiments that have been done. Okay? So the thing to say about this is that obviously some of these are much harder or easier than others, right? Imagine we're dealing with 5-meter sized objects. Okay, so that's actually, potentially an interesting size in protoplanetary disks. Obviously, an experiment colliding together 2 5-meter sized rocks or something like that is not a very easy thing to do, right? At the very least, you want to be careful with health and safety, right? So there are sort of regions of this parameter space that are experimentally very, very difficult. Okay, and so in more recent years, what people have been doing is not trying to just sort of map out this whole parameter space, which involves many orders of magnitude, and some of it's very difficult, but rather to ask, given sort of realistic conditions in disks, which pieces of this parameter space are really the most important to map out. And that's been actually a substantial advance. Okay. However, if we sort of step back then and ask, well, what are the main results? If we deal with really small dust particles, then actually that sort of simple argument I gave a couple of slides back, small dust particles have a lot of surface area relative to their mass. When they collide, surface forces are generally quite efficient at making them stick. So if we're really just thinking about micron-sized particles, saying that they're perfectly sticky is almost a good enough approximation. We don't actually need any more complicated or detailed physics. Okay, so that's good. So we can go from the small size, the very small sizes, up to small macroscopic sizes without really having any material barriers to worry about. Now, once we get to millimeter sizes, though, things are a little bit different. Okay? And if you have silicates, so if you have rocky materials, high temperature condensates, it appears that there's some preference for those objects to bounce at the kind of realistic collision velocities that you would have for those particles in protoplanetary disks. So that might be a problem for building larger objects if you're, let's say, within a few AU of the central star. If you have ice, on the other hand, that can grow to larger sizes. Okay, so the sort of, let's say, common sense view that ice is going to be stickier than rock does appear to hold even under the conditions which are somewhat different in disks. And then if you have very high velocity impacts that are quite unequal, those can actually lead to growth. That's a little bit counterintuitive, but you can maybe think about that in terms of sort of much larger things that are colliding and producing craters. Right? So imagine you took the moon and you collided it at extremely high velocity with another moon-sized object. Okay? Well, if the total energy of the collision was vastly greater than the gravitational binding energy of the two moons, then you would expect that you might be able to just blast the two things apart into a million small fragments. Okay? But suppose you instead took the moon and you took a meter-sized object and you collided it into the moon at also very high velocity. Well, in that case, it would create a crater, and a little bit of stuff would be blasted back into space, but nonetheless, most of the mass of the impactor might actually get added to the moon. Okay? So that's true at large sizes. It also appears to be true when you're dealing with things that are more of millimeter and centimeter size. So if you have sort of moderately sized objects and a lot of very, very small objects, micron-sized, and they collide very fast, then actually you can actually grow in that way. So it's a little bit of a complicated situation. But if we had to summarize it with just the two numbers, the fragmentation velocity, the velocity at which collisions will typically lead to breakup, seems to be about 1 meter per second for rocky materials and maybe an order of magnitude larger than that for icy materials. Okay, so actually these are velocities that are, of course, quite comparable to sort of terrestrial velocities that we know about. Okay, so those were some collision physics. I now want to say something just briefly about radial drift. And so if we have particles that have significant aerodynamic coupling to the gas, we predict them to spiral inwards. Okay? And the way to think about this, as I've already mentioned, here we have the gas disk, and the gas disk has some radial pressure gradients. Okay? So for the moment, let's assume that the pressure gradient is such that we have high pressure in the inner part of the disk and low pressure as we go to larger distances. So the pressure gradient is acting outwards. It will be partially supporting the gas in the disk against the force of stellar gravity. So as a result of that, the velocity of the gas in the disk is a little bit smaller than Keplerian. Okay, we've already noted that. Now, if we have a large solid body, it will, on the other hand, be just moving at the Keplerian speed. So here's the large body. It's moving at the Keplerian speed. The gas around it is moving a little bit slower. Okay? So the gas will be coming into this solid body. It will feel a headwind. The aerodynamic drag will remove some angular momentum, and then this large solid object will spiral in towards the central star. Okay. Now the same thing's true if we have a very small object. Okay? Now if we have a very small object, the argument has to be a little bit different. Suppose we have a dust particle that has tau sub s that's much less than 1. Okay? Well, in that case, it won't be moving at the Keplerian speed because the tight aerodynamic coupling means that it will be being swept around at the same speed as the local gas. Okay? However, the particle still doesn't feel a gas pressure gradient, even though it's moving at the same speed as the gas. So for the particle, it's actually moving too slowly for its centrifugal force to balance the inward stellar gravity. So for that very small particle, which is moving at a sub-Keplerian speed, it will start drifting towards the star, basically at its local terminal velocity. Okay? So whether we're dealing with a very small particle or a very large one, the answer is the same. It always moves inwards, though if you like, for somewhat different reasons. Okay, so you can work this out. Let's imagine we have this force balance in the gas. So the gas azimuthal velocity is basically balanced by the stellar gravity, but then we have this small component which is due to a radial pressure gradient. Okay? Let's say that the midplane pressure is some local power law with some index n. Then we get a simple expression for the difference between the Keplerian velocity and the local azimuthal velocity of the gas. Right? It's, as I said before, it's second order in the ratio of the sound speed to the Keplerian speed, which is just the ratio of the disk scale height to the distance from the star. Okay, so this is this small, few tenths of a percent sub-Keplerian velocity headwind. Okay, so how do particles behave in that? Well, we just consider equations for the radial velocity and the azimuthal velocity now of a particle. So these V's represent particle velocities, which is embedded within this gas. Okay? And the key point is that both in the radial and in the azimuthal direction, we have frictional forces, aerodynamic forces, which depend, of course, on the velocity difference between the particle and the gas that it is embedded with. Okay? So what we need to do, so this would be generally true for any friction time that the particle actually has. Now, you can solve those equations just in general, but in most cases, what we're interested in are circumstances where actually the particle has almost a circular orbit, and it's really spiraling in relatively slowly compared to the orbital speed towards the star. So you can make some simplifications, which are gone through in the notes, and come up with a very compact expression for what the radial velocity of this particle works out to be. And it has this form. Okay? So VR gas is the radial flow of gas within the disk. So that's the rate at which, let's say, accretion is bringing the gas towards the star. And eta here is this ratio that's basically the thickness of the disk divided by the radius squared, with some prefactor which depends on what the power law gas density structure looks like. Okay? And here we have the dimensionless friction time, which is the same as this stopping time, which I defined before. So what you can see is that there's this symmetric part on the bottom, the friction time, plus the inverse of the friction time. And what that means is that this radial velocity actually peaks when this friction time is 1. Okay? So the situation that's exactly intermediate between the two simple limits I kind of sketched out in words: a really big object that's feeling a headwind and a really small object that is orbiting with the gas and settling at the terminal velocity. Those are sort of the end members, and right in the middle is the point actually where this radial drift is maximized. And here's what that expression looks like for some reasonable parameters. So here's this dimensionless friction time or stopping time, and here's the radial velocity compared to the Keplerian velocity. Okay? So what you can see is for very small particles, those are just being dragged in by any radial flow of the gas. So this speed is the speed at which in this, this model I've put together, the gas is flowing towards the star. And then as we go to very large objects, those are just moving at the Keplerian speed, and the aerodynamic forces ultimately become negligible because the mass becomes large compared to the surface area. So ultimately this just keeps dropping down towards zero. But then there's this large peak in the middle, which is at tau friction or tau stop of order unity. Okay? So we have a peak in the drift speed at tau of 1. Okay. So what's interesting and potentially problematic is that this timescale is quite fast. Okay? So we can actually see that. If we go back, there we go. You can see that directly in this plot. For this friction time of 1, this radial velocity is about 10 to the minus 3 of the Keplerian velocity. And that is basically the same number we had for the difference between the gas orbital velocity and the Keplerian speed. Okay? So it's a small number, right? 10 to the minus 3. You might sort of say it's a negligible number if you just think of it in those terms. However, if we're just at 1 AU, the orbital speed is, the Keplerian speed, its orbital time is 1 year. So if we're drifting in on 1,000th of that time scale, or 1,000 times that time scale, we will drift in 1,000 years. So we will lose material onto the star in a very, very short time scale compared to the lifetime of the disk. Okay? And this is described as the meter size problem or the radial drift problem. If we have objects that have this dimensionless stopping time of order unity, physically those would be roughly meter-sized objects at 1 AU. We would predict that they drift towards the star very quickly and would ultimately get into the hot regions of the disk. They would evaporate or in some other way be lost into the star. Okay? And here it's just shown as timescales, time in years, distance in AU. This is for some assumed thickness of the disk. This central line this lowest line is for a friction time of 1. Okay? So the survival time of solids in the disk is potentially sort of worryingly short. Okay, okay, so what's going on here? Obviously, if we want to we know we must be able to make larger objects than things that are just meters, because we're sitting here. So somehow material must be able to grow from small sizes, where the radial drift problem is not too severe, to large sizes, where it's also not too severe, pass through the dangerous region in the middle, without all the stuff just spiraling into the star and getting lost. Okay. So logically, there are various solutions to this problem. One is that planetesimals, so kilometer-sized objects, form fast. And that would be the obvious conclusion to draw from having this radial drift problem in the first place. And they could grow fast, obviously, if collisions are extremely efficient. So whenever anything collides, it coagulates. That would obviously be the best circumstance for doing things with collisions. Or they can do it if we have collective instabilities which lead to gravitational collapse, which I will say more about later today and tomorrow. Now, generally, people tend to think this second solution is more plausible than the first. Okay? And the reason for that we've already discussed. Actually, experiments show that at least for rocky materials, collisions do not typically lead to sticking very efficiently once we get to sizes that are, let's say, of the order of centimeters. Okay? So it seems hard to go to kilometer sizes just by colliding pairs of objects and them sticking together. Now, there's another possibility, which is that this radial drift occurs because the pressure is highest in the middle of the disk, lowest in the outside. So there's a pressure gradient, which means that the gas is going slower than the Keplerian speed, and so objects feel this headwind. Okay? Suppose we had a circumstance where locally we had a pressure maximum in the disk. Well, in that case, in some places within that pressure maximum, the gas would actually be going faster than the Keplerian speed. And in that case, the whole argument I've given for why the particles would be drifting inwards would just be reversed, and the argument would be that the particles are drifting outwards. Okay? So if we have a local pressure maximum, actually material could collect at that point, and it wouldn't have a tendency, at least under aerodynamic forces, to want to go either inwards or outwards. So in that case, we could wait, and even if it takes longer to build large objects, we don't have such a problem. Okay? So this is another possibility, which instead of sort of being based on, let's say, the physics of the solids, would occur if there's some interesting physics going on in the gas, some reason for having these local pressure maxima within the gas disk. Okay, so this is just discussing this first possibility of collisional growth. Can we get this fast collisional growth? And the problem here is that obviously it depends on the velocity of the collisions as well as the things that they're made of. And the velocity of the collisions often is determined by the presence and the strength of turbulence within the disk. Now that's a factor which we can to some degree imagine might be uncertain. So maybe we can wind down the turbulence, make the collision velocities due to the turbulent component smaller. But the problem is that suppose we have a collision between a particle with a dimensionless stopping time of 1 and one which is significantly smaller. So it has a smaller dimensionless stopping time. Okay. Well, in that case, the collision velocity will have a component, which can be actually a large component, which will be coming from the radial drift itself. Okay. So the large particle will be drifting radially quite fast, the small particle much slower. So even if there's no turbulence to contribute to their collision velocity, they can have quite a large collision speed just due to the radial drift. Okay? So this speed can easily reach many meters per second, 10 meters per second perhaps, and so that is probably above the fragmentation velocity, at least for rocky particles. Okay? So because of the radial drift itself, many collisions we think would lead to bouncing or fragmentation. So this is sort of the, let's say, the qualitative argument for why we think fast collisional growth doesn't work very well in the disk environment. And that's also what's seen then in much more detailed calculations. This is again from this annual review of Bloom and Verm. Here are the experiments that have been done up to that point, and they're color-coded here by whether in those collisions you got mass growth, basically you were neutral, or whether you got mass loss, whether you started actually breaking particles apart as opposed to sticking them together. Okay? So blue is good. Blue is a region of parameter space where collisions lead to growth. And orange and red and yellow are places where you get fragmentation and mass loss on collisions based on experimental results. And these experiments are all for rocky materials. They're all for silicates rather than for ices. And the point is just the one I was making earlier. For small objects, things are generally pretty favorable. Collisions tend to lead to growth. However, for larger objects, as you can see, there's a lot of red in this diagram. So whether you imagine things are going via collisions of equal mass objects, then you'd be going diagonally in this diagram. Everything's good until you get to about 10 to the minus 2 meters, about a centimeter, and then you're encountering these yellow and red regions where the collisions wouldn't lead to growth. Okay? Now maybe you think you can bypass that with very unequal mass collisions, so you start to go vertically or horizontally in this diagram, but then again you're reaching these orange regions. Okay? So if you think you want to do everything with two-body collisions, you have to hope that there's some sort of blue areas in the parts that have not been mapped out very well experimentally. Okay? Otherwise, it sort of seems you've got a barrier which is coming like this, and it's really difficult to get beyond small macroscopic sizes as a result of collisions. And that's what people who do models, simulations of this find. So these are either Monte Carlo or coagulation equation solutions. So this is size, and this is a number of particles of a given size. These plots of different models and different times. It seems to be quite difficult to get beyond, let's say, small macroscopic sizes that are of the order of centimeters. So we think that the processes of collision and fragmentation that are taking place within protoplanetary disks will basically set up some almost quasi-steady state size distribution where we have some small dust particles that are being produced by fragmentation. We have a larger number of, let's say, millimeter or centimeter sized particles which have been produced via accretion. And collisions that are leading to larger objects are basically being locally balanced by collisions that are breaking things up into smaller things. So we have a population of particles in the disk, but the collisional processes on their own are not leading to the growth of meter-sized objects or larger-sized objects within that environment. Okay, so I think this is a logical place to stop. So we'll talk tomorrow about how we might be able to solve this, but for the moment I'll just leave this as a puzzle. How do we actually get beyond these small sizes to build the planetesimals that will ultimately be the building blocks of larger planets? Okay, questions?
So, you might talk about this tomorrow, but is there the equivalent of the two-ray cube, but for dust particles?
Yeah, so the question is there the equivalent of a two-ray cube for dust particles? And so yes, yes there is. So, at the simplest level, you could just take the two-ray cube for the gas and replace the sound speed with the velocity dispersion of the particles. Okay, and exactly that wouldn't quite be true, but basically that would be a reasonable approximation. Now then it will be modified in sort of, well, there'll be two other things to say. One is that there's a simpler condition in some sense, which is just the Roche density condition, which says that tidal forces are not going to break the object apart against its self-gravity. So that's in fact a simpler condition also for gravitational collapse of solids. The other is that if the system has both solid material and gas, sort of in equal, sort of comparable amounts, then that can sort of give rise to some interesting extra things. So then the equivalent of two-ray Q needs to include both components, and it's not simply a simple addition of the two parameters.
Yeah. Are static forces perhaps important at all in coagulation of solid grains? If there's enough static.
You mean like charging forces? Yes. Okay. So the question is, are electrostatic forces, or I guess magnetic forces, potentially, important in these processes? I think the answer is probably not. Okay. Basically because they could be important for very small dust grains, right? So Drain and others have developed theories for what the equilibrium charge on dust grains of given size should be, right? And so obviously the basic picture is that you have a dust grain, and actually it can be quite efficient. Electrons can stick to the surface, and the dust grain becomes charged. But then obviously as it becomes charged, it develops a barrier to further charges sticking it. So it reaches some kind of equilibrium charge. So for very small dust particles, that charge could be significant and affect the coagulation. But for the small objects, basically they're going to stick anyway. And once you start, I think, getting to millimeter sizes, you've just got too much mass relative to the surface area for the equilibrium charge to have a large effect on the collision dynamics.
What about, could it affect the distribution of the gas in the early stages when it's small?
So the question is, what about when we're thinking with small particles? Could there be magnetic or electric effects taking place there? It's not been looked at very much, right? I think there could be places where it would matter. Suppose you're interested, say, in scattered light images. So you're really thinking of micron or submicron sized particles. Those are at high density regions. They may actually be exposed directly to UV, so they may have some charging due to that. So say if you're interested in what's happening near the magnetosphere, right, where you've got a strong magnetic field, then I think it's quite likely that there could be some interesting physics there. But it's not a topic that I would say has really been explored very carefully, at least not to my knowledge.
Is it possible to detect decimeter and meter-sized bodies in protoplanetary disks?
Yeah, so the question is it possible to detect these, let's say, decimeter or meter-sized objects in disks from an observational point of view? And no. No. So basically, the furthest you can go observationally, just trying to think if there's any exceptions, but the furthest you can go observationally is maybe about centimeters. Okay, so millimeter-sized grains, the thermal emission is very strong, and that's dominantly what we see. Centimeter-sized objects obviously would have thermal emission of their own, which is smaller because of the surface area. You can look, say, with centimeter wave radio observations, say with the VLA, and in principle, those are certainly deep enough to detect the thermal emission from centimeter-sized bodies. However, the problem is that when you get to those wavelengths, there are also non-thermal processes from basically the hot gas surrounding the disk. And it starts to become difficult to distinguish the thermal emission from the particles from just non-thermal emission in the gas around the star. And once you get to tens of centimeters, it's basically a hopeless task. So even with very high sensitivity, there's really, as far as we know, I think no way of observation saying something about that. I guess the only analogous place where you could say something is obviously Saturn's rings. We do know something about the size distribution in that size regime directly in Saturn's rings, but the collision physics there is a little bit different from the disk situation.
Yeah. Are there any temperature-dependent effects on collisions, perhaps near to the star, where things might melt, become more formable?
Yeah, so the question is, are there temperature-dependent effects on collisions? It's been discussed a little bit, mostly for ice, because actually, there are some effects of that kind. I've heard it said, at least, that if you throw a snowball at a window, obviously not too hard, so you break the window. If you throw it there, then you can sometimes get it to stick, and that is actually due to these kind of like pressure melting and so forth when you hit, right? So those kind of things obviously matter the most if you're in sort of marginal circumstances where you're not way below the triple point of the system. Okay, so there could be some such things, and also perhaps relevant is rocky material is maybe not very sticky, but you could imagine coating it with a layer of organic material, and then maybe it would be more sticky. So there's actually a whole bunch of sort of only partially explored possibilities. A lot of what's been done has been driven by the fact that silicate materials are easy and safe to handle. Ices are safe, water ice is safe, but harder to handle because it involves low temperatures. Organic materials, you need to be more careful about safety in the lab. So there's a lot of things that could be taking place that we don't know very much about.
Is there any places where you have to worry about genes instability?
Other places where you have to worry about genes instability? Yes, I mean, at least in the solid form, and actually I'll say more about that one tomorrow, because I think these collective effects that I was sort of been alluding to basically lead to gravitational collapse. So that's the route one goes in that direction.
To what concern temperature? Because I assume that at certain point of the disk evolution, the star begins to make nuclear reactions. So I imagine that also the pinging radiation on the disk may help or not to form planetesimals and aggregates of dust. So at first guess, I would say that maybe fainter stars have helps to keep the temperature low. So if this may be helpful for something or not, what do you say?
Yeah, so the question is, what about the changing temperature structure of the disk due to the stellar evolution, the pre-main sequence stellar evolution? Well, so I guess the most basic question is going to be where you're going to actually be able to have ices versus silicates, right? So that's what we describe as the snow line, and in the solar system we think was at about 2.7 AU. Okay, now 2.7 AU is actually quite far out, and so to make the snow line that far out, you actually need quite a lot of accretion. So we think that the position of the snow line, at least in the solar nebula, was that far out because gas was accreting quite vigorously. And it's actually an interesting question why that is a fairly sharp division, because as you say, both the stellar luminosity and the accretion luminosity from the disk would be expected to be quite strong functions of time. Okay? And generally what you'd expect is that the snow line would move in as accretion becomes less, but then when the disk eventually becomes optically thin, it would actually move outwards again as it really sees the stellar irradiation. And in the solar nebula, in the solar system, we don't see sort of any sign that process happened, but obviously it must have happened, and that could be important, right? But exactly, yeah, there's a little, actually some little some puzzles there based on what we see.
Okay. Welcome.
Fine. Do we expect new dust grains to be formed in protoplanetary disks? Is the transition between gaseous and solid phases important?
Yeah, so the question is, do we expect new dust grains to form within disks? And so that actually sort of comes back to the previous question about really the thermal evolution, right? So if we imagine we have some species in the gas phase, right? It will obviously, in principle, thermodynamically want to condense if its vapor pressure becomes too large, right? So then it will be favorable for it to condense. And there's some complicated condensation physics, but generally it will do so. So the circumstance where you would expect a lot of new stuff to be formed is if you have a hot region with everything in the vapor, and then you cool it. So if the accretion is very unsteady, so you heat it up and cool it and so forth, then you'd expect sort of cycles of sublimation and recondensation to occur continually. And it can also occur actually at this snow line, because there you have a gradient of vapor, and so the vapor will be trying always to diffuse outwards, and it will then be prone to condensation, either into new dust grains or onto the surface of grains that are already present.